Section 9.2, Analyzing Rational Functions. So today, we'll analyze rational functions a little bit further than transformations. We're going to determine whether there is points of discontinuity or vertical asymptotes occurring. So point of discontinuity is a new vocabulary word for us. It's a point that is described by an ordered pair which the graph of a function is not continuous. It occurs in rational functions when its rational function can be simplified by dividing the numerator and denominator by a common factor that includes a variable. This results in a point missing from the graph, which is represented by using an open circle. So we're going to consider two functions here. This first one, y equals x plus 1, obviously is a linear function. And then we have an x squared minus x minus an x minus 2 is a rational function. If we compare their domains and range, our linear function would be all real numbers. If we factored this expression, we in the numerator get an x minus 2 times x plus 1 all over an x minus 2. Our non-permissible value for the function not equal to, which then creates our domain being all real numbers where x cannot equal 2. And then because these two values cancel, these two factors can cancel, we end up with a very similar graph to our linear function. We get the same expression left over. So in fact, our rational function and linear function are both going to look like a line graph, okay, with the same x-intercept, with the same y-intercept. The only difference between the two is the point of discontinuity that occurs. And so that point of discontinuity is going to occur when x is equal to 2, because that's our non-permissible value. To find the y value, if we take this non-permissible value and substitute it in to the simplified equation of our rational expression, we get a value. So our range is now going to be all real numbers where y cannot equal 3. So that's how we get that 3 value. So therefore, we're going to have this point of discontinuity occurring at 2, 3. So this is going to be represented by a linear function of just x plus y, and this is going to be represented by the linear function not x plus y, but x plus 1. But this function, when x is 2 and y is 3, we're going to have a point of discontinuity. So what we're going to have here is like a hole in the function instead of just a straight line. Okay, but sometimes most of our calculators won't even show that point of discontinuity. You'd have to go to your table of values to identify it. Okay, all right, so let's look at compare two more functions. So compare the behaviors of the following functions. So x squared minus 2x divided by a 4 minus 2x versus an x squared plus 2x divided by a 4 minus 2x. So I'm going to algebraically explain this as I work through this problem. If I look at this first function, if I factor my numerator and denominator of this function, I get x bracket x minus 2, factor out a negative 2 in the denominator of my other value, and I'm left with the same expression. So what I'm left with here is when this is factored, I can talk about the non-permissible value of this function, which is x cannot equal 2. Similarly, if I factor this second function, factor out an x, I'm left with an x plus 2. Over same thing, I'm going to factor out a negative 2 in my denominator, and I'm left with an x minus 2. My non-permissible value in this case is also an x cannot equal 2. So the two functions have the same non-permissible value, but let's talk about the feature that happens at this non-permissible value. In this case, because these factors cancel, this is represented a point of discontinuity. Because in this function, because the two factors do not cancel, this non-permissible value is going to be represented by a vertical. Okay, and so to determine the behavior near that non-permissible value, we want to think of as the graph approaches those two values. And so for your point of discontinuity, what we can do is substitute in our value, our non-permissible value, into our simplified function. So this function simplifies to an x over negative 2. If I substitute a 2 into here, this tells me the behavior near the is going to approach at a y value of 2. So this is approaches negative 1. Here, if we have a vertical asymptote occurring at 2, then what happens is the behavior near this non-permissible value is going to approach positive. Okay, so point of discontinuity, it should actually approach a value, whereas an asymptote is going to approach positive or negative infinity. So now if I were to sketch this function, again, this simplified function ends up to be, if I were to rewrite this as negative 1/2 times x, this ends up to be a linear function in the form of mx plus b. My y-intercept would be 0, so if I plotted a point at 0, 0, the slope of this graph is negative 1/2, so negative 1 over 2. But we know at this point, this is our point of discontinuity, so I'd leave an open dot at that point. Or I could have went up 2 and to the left 2 to get another point. So then if I connect my 3 points, I actually don't want to run my line through that point of discontinuity. I'm actually lifting my pencil and continuing the graph. So we actually get a hole happening on this function. All right, and then this second function, what does it look like? A little bit different. When the degree of the denominator is less than the degree of the numerator, a slant asymptote occurs rather than a horizontal. So if we were to look at this function, and we don't actually study slant asymptotes in Math 30, I wanted to show you an example to show you that they actually do exist, but we actually don't study them. Okay, so all the examples you'll be given or tested on will be just horizontal. So if I were to graph this function, if you look, we have this vertical asymptote occurring at 2, but then we have a slant asymptote as a guideline to get our function. So if you notice, our slant asymptote kind of looks like this. And this is a guide that our graph is going to approach. So our function looks something like this. So like I said, you're never going to be asked to identify those slant asymptotes. But just be aware that if you come across something where the degree in your numerator is larger than the degree in the denominator, that's actually going to create a slant asymptote, not a horizontal. Okay, so a horizontal asymptote occurs when or the degree in the denominator is greater than the numerator. Okay. So again, just to reiterate again, if a factor is in the top and bottom that can be cancelled in our rational expression, this creates a point of discontinuity. If a factor is only in the bottom that cannot be cancelled, this is going to create a vertical asymptote. Okay. All right, so next we're just given 6 rational functions. We're going to try to identify them to its appropriate graph without obviously graphing them. So the first thing we're going to do to all of these is we're going to quickly factor all of my numerators and denominators. So here I can factor out an x. Bottom is a difference of squares. B, I can factor out a 2 in my numerator. The bottom can't be factored at all. There is no difference of squares. Can't factor a sum of squares, sorry. C is a difference of squares again. Question K, the top cannot be factored, but the denominator becomes an x minus 2x plus 1. L, the denominator is a difference of squares again. M, the top factors to be an x minus 2 and x minus 3. And then in the denominator here, because this is very similar to an x minus 3, I'm going to factor out a negative 1 here, and I'd be left with a positive x minus 3. So that those values are going to cancel. So now in each one of these, I'm going to identify, is there a point of discontinuity, where does asymptote occur, and if need be, talk about intercepts as well. So in this first function, my x plus 2's cancel. So my non-permissible values here are x cannot equal plus or minus 2. The positive 2, so I call it pod for point of discontinuity. Point of discontinuity at x equals negative 2, and then v dot a, vertical asymptote, at x equals 2. So now I'm going to search in my graph is where do I see a point of discontinuity at a negative 2? Right, here we go. Point of discontinuity at negative 2. Vertical asymptote at 2. So A is going to match up with graph. So this is graph A. All right, let's look at question B. I look in my denominator, non-permissible values. Oh, there are none. There is the only value that I could add to negative 1 to equate this to 0 to add to a positive 1 would be a negative 1. And I'm squaring every x value. Anytime I square a number, I'm always going to get a positive. So this will never create a 0 in the denominator. So there are no non-permissible values. So that tells me there's no points of discontinuity and there is no vertical asymptotes. So which graph has a fluid graph, right? The domain here would be all real numbers. So which graph identifies that would be graph number 3. So this matches with B. All right, graph C. Right, my non-permissible values are x cannot equal plus or minus 2. Neither of them cancel, so that means I have a vertical asymptote both at positive 2. So which graph does that line up with? Negative 2 and positive 2 would be graph A, so this has to be matched with C. Question K, again, my non-permissible value is x cannot equal 2 and a negative 1. Neither of these factors can cancel in my numerator, so again I have two asymptotes, one occurring at x equals 2 and a second occurring at x equals negative 1. So which graph does this match up with? Positive 2 and a negative 1 would be graph 6, so this would be K. L, my x minus, so let's talk about non-permissible values first. X cannot equal a positive or negative 1. My x minus 1 cancels, so this tells me I have a point of discontinuity at x equals 1 and a vertical asymptote at x equals negative 1. So I'm going to find that graph, point to discontinuity at a positive 1, vertical asymptote at negative 1, so this has to be L. So obviously the remaining graph is going to be 6 or M, so let's find out why. My x minus 3's cancel. My non-permissible value is x cannot equal 3. There's nothing left in my denominator, so this simplifies just to a negative x minus 2, which creates a linear function, but we should have a point of discontinuity at x equals 3. So linear function, point to discontinuity at 3. This is going to match up with graph M. Okay? Okay, and then lastly, example 3. It's determine the equation of the graph on the right by starting with transformations and answer in a single simplified expression. So first thing we want to do is kind of identify some obvious things that are happening. X-axis, this is the y-axis. Here is a vertical asymptote. So each of these the scale goes up by 2, so this is 2, 4, 6. I have a horizontal asymptote at y equals 1, kind of an horizontal asymptote at y equals 1. I have a vertical asymptote here, and look, my horizontal scale goes up by 1s, not 2s like my y, is at x equals -2. So we have a vertical asymptote at x equals -2. And then my point of discontinuity is at 0 comma something. So the x value of my point of discontinuity is at 0. So I'm going to start by creating my function here. So thinking back to our transformation day, we started with a function that looked like this, where a is our vertical stretch, which we are going to, that's the last thing we're going to find. H would represent our vertical asymptote, which is our horizontal translation. So H would have to be a -2. And then our K value would have to be our horizontal asymptote, which is 1. So if I start by substituting this in, okay, so here is my function so far. Sorry, I'm just gonna move this over. Okay, but one thing I did not account for is this would be my simplified version after I accounted for my point of discontinuity. So we haven't accounted for my point of discontinuity. And remember, your point of discontinuity is a x, or that cancels in my numerator and denominator. So if that point of discontinuity, my x value is 0, then what value, this would be my non-permissible value. So my non-permissible values for x would be x cannot equal 0 and a -2. So I've accounted for the -2, but I haven't accounted for the 0. The 0 would mean that this would have to have a fact expression of just x. So here's my 0, here's my -2, but we know this value is always going to cancel to create this point of discontinuity, so I need an x in my numerator. All right, so here is my function. Okay, now all I need to do is find my stretch value of my function. Well, how do I do that? Find another point on your graph that you can clearly identify to substitute in for x and y, which would be this point. So this is on the x-axis, so this point would be -6, 0. I'm going to substitute this in for x and y. So y would be 0, x would be 6, so I'm going to substitute that in 3 different times in this equation, plus 1. Let's simplify this. So we get a -6a in my numerator. This equates to -4 times a -6, ends up to be 24 in my denominator. So now I'm going to solve for my a value. So I'm going to subtract 1 from both sides, cross multiply my 24, and divide by 6. So my stretch factor ends up to be a 4. So my transformed function ends up to be this. The question asks us to then answer in a single simplified expression. So a single simplified expression means I need to combine these. I need to actually add these into a single fraction by getting a common denominator. So I'm going to multiply my 1 by an x times an x plus 2. This is all going to be over this denominator of x times x plus 2. I'm going to run x through my set of brackets. And then I'm going to collect like terms. So my final rational expression would be x squared plus 6x all over, and you could run this through your brackets in your denominator or not, over an x times x plus 2. So that would be your final simplified single expression.